So these values will be used later on in QGIS plugin to calculate the relationship correlation linear coefficients between land surface temperature and the temperature difference between two heights, 0.1 and 2 meters, for cold and hot pixels. This plugin uses an iterative process for obtaining these coefficients. This relationship is necessary to estimate sensible heat flux for all pixels and finally to find latent heat flux related with evapotranspiration. So let's start to import climatic factors. So we will use this image collection, land daily aggregated climate analysis. It's dataset availability until 2023, so it's until now. So it spans dew point, temperature 2 meters, and we also will need surface pressure, so this one. So let's first import, copy and paste. So we need from only for one image so far, so we need for date 0.3, and 0.4, let's say 3. So and we need to select this so we need temperature, let's copy it, and we need surface pressure. So now let's create variable for surface pressure. Let's name it this one, not dataset but image. Select surface pressure and rename it to pressure. So atmosphere temperature, again image, select and rename it to air temperature. Now pressure for cold pixel, image, select surface pressure, sample, cold 30, first, So let's print p cold number p cold, and as well for the cold temperature of the atmosphere for the cold pixel. So sample first get temperature. So also print TA cold and now let's compute our density for the cold pixel. If you remember from the formula, so it's a gas constant and this is a molar mass of dry air, so we will use them in our expression. So multiply molar mass to pressure for cold pixel, and also multiply and divide it to the multiplication of this gas constant to the atmosphere. And of course let's print density RHO for RHO cold. Let's save it and run it. So let's run it. So this is my air pressure at the cold pixel, temperature in Kelvin at the cold pixel, temperature of the atmosphere at the cold pixel, and air density at the cold pixel. So we need just the same, repeating the same steps. We need to compute the pressure, air density, and temperature of the atmosphere for the hot pixel. So I will pause the video here and and replicate the same steps for the hot pixel. You can also pause the course video here and just try to repeat the same steps independently for the hot pixel. So for the hot pixel, again I computed the surface pressure for hot pixel and print as hot and temperature of the atmosphere for the hot pixel as well. If you remember, hot and cold. And I computed for air density for the hot pixel, using this expression and just these variables. So let's save it and run it. Let's see what we get. So pressure for the hot pixel is the same with the cold one. Temperature slightly differs for the hot pixel, and air density also slightly differs for the hot pixel, but just this is for one image.